Okay, back to measurable functions. Let's suppose that we have that f is a measurable simple function, which I shouldn't have put the word measurable there because if it's a simple function, it's measurable. Just to remember, recall what a simple function is. I forgot my coefficients here, but it's a linear combination of characteristic functions. So all of these sets En are measurable sets. If I define lambda f, which is a function of f, of any measurable set to be in the mu, so mu is a measure and E is a measurable set under this measure. If I define lambda f to be the integral of f of E d mu, which we talked last time about what is meant by the integral of a simple function, then it turns out that this object here is also a measure. How do I prove that? Well, first I have to show lambda of the empty set is 0. I just go through the properties. So by definition, lambda of the empty set on a characteristic function, for example, is equal to mu of E intersect empty set. Where does that come from? Well, I'm skipping a lot of measure theory, but if I'm integrating over a measurable set A, the characteristic function of E of x, then the integral is the measure of E intersect A. And you can draw diagrams to show that this is what you're going to get to. So E intersect empty set is a subset of the empty set, and the measure of the empty set is 0. Now that I have it for a characteristic function, I need to show the result for a simple function. This is a pretty standard procedure in measure theory to prove some of the basic results. So if I integrate over the empty set, and this time I do have my coefficients here, thank goodness, and I look at the linear combination, this is my simple function. Well, there's a theorem, which I skipped, that allows you to pull a finite sum and integral apart. So these two swap, and I'm really integrating these guys over here. But I know from my characteristic function that this piece over here is equal to Ci times the measure of Ei intersect the empty set. I also know from the previous calculation that each one of these measures are 0, so the entire sum of these measures turns out to be 0 as desired. I don't know what order I had the properties of measure, but obviously you need to have this non-negative. But you know, when we first defined our integral, the simple function itself was non-negative, so it's obvious. But in a real analysis class with a probabilist as your teacher, you're going to have to prove these kind of details. Because we're in a PDE class, we can skip some of these details. And I'm very sloppy. I think my real analysis teacher would have me if he knew that I was skipping all the, let f be a simple function. This means that f can be expressed as a linear combination of Ci characteristic function times Ei, where I equals 1 to n represents measurable sets, and so forth. I'd have to put in all my epsilons and deltas and make sure it was clean. So this is a very sloppy argument. Of course, this is always the most difficult to prove, that we want to show that for a set of disjoint sets, that the union, the measure of the union is really the sum of the measures. It's not that hard to prove. I'm going to give you the steps of how to prove it and suggest that you prove it for exam 3. You want to first prove this result for just a characteristic function. Maybe a sum of two characteristic functions just to get the feel. And then you want to look at this in terms of, again, you're going to get intersections, and so it's kind of a similar cut up as what we've had before, and you'll slowly break down the pieces, and you do need to draw a Venn diagram to see what happens in certain cases. So feel free to do this one. It's a nice exercise. Put it on exam 3, and you're definitely welcome to show me any side work that you have. Some more properties of Lebesgue measure. these are monotone properties. I'm actually setting us up for the monotone convergence theorem. And here's one that if I have a sequence of measurable sets, and I know that one is contained in the second, is contained in the first, they're monotone increasing sets, then the measure of the union is the same thing as the limit of the measures. And that's the same thing as the sup of the measures. So really, it turns out to be the largest, or in limit, it turns out to be the largest of all the measures of these sets. Likewise, in reverse, if I have E1 is the largest set and all the others are contained like a nested babushka doll, then I can, then this measure of this intersection exists, and it turns out that it's equal to the limit, and which is really equal to the infimum of all these mu's. And just to remind you from real analysis class, the infimum is the least upper bound of your sequence or your set. You can think of it as a minimum, but the criteria of the minimum is the minimum has to be attained. For example, the sequence 1 over n decreases to 0. The infimum is 0, and there is no minimum inside that set that's attained. So the infimum is exactly the least upper bound, and the supremum, the sup, is the least upper bound. So if you're playing limbo sticks with your sequence, it's as low as you can go with your limbo stick with as an upper bound. So now we're heading towards the concept of monotone convergence. If I have a function and it's a positive real valued function on the extended reals and it's measurable, then I know that there's going to be a monotone increasing sequence of measurable simple functions. And what I mean by monotone increasing is that if I fix an x, the fn of x is smaller or equal to fm of x if n is less than or equal to m. So they're gradually getting bigger and bigger. And they're non-negative measurable simple functions that converge pointwise to f of x. So every f of x, I had mentioned this before, every f of x can be expressed as the limit of a sequence of simple functions. Not only a limit of a sequence of simple functions, but a limit of a sequence of monotone increasing simple functions. And this is actually really important because I've shown you the algorithm of how we prove results. We first prove it's true for a characteristic function, then we second prove it true for a simple function, and then the next step is if you have a measurable function, you can express it as the limit of a monotone increasing sequence of simple functions. But and I'm going to give you one huge theorem which is going to depend on the fact that we have a monotone increasing sequence of measurable functions, and that one property or that one theorem will allow you to prove all sorts of nice results in measure theory on Lebesgue integration. So the implications are actually very huge. So I restated it just the way I said it in the previous slide. Every non-negative measurable function has a sequence of monotone simple functions that converge to it. And this provides us with the algorithm for proving results for measurable functions or on Lebesgue integration. The first step is to prove it true for a characteristic function. The second is to prove it true for a simple function. And you prove the general result by writing f as the limit of a monotone increasing sequence of simple functions.